Here's the first of the sessions which we're going to combine. We're going to do 3.2, Chapter 3, Section 2, and we're also going to do Chapter 3, Section 3. You can tell immediately that these are reviews. You've already learned about functions in a previous course, and of course graphing, and simply graphing ordered pairs. This one I think we can breeze right through. Let's give it a try. So we'll graph ordered pairs. So we'll have x and y, and when we place these on a coordinate plane, we're going to go horizontally with x and vertically with y. Determine whether an ordered pair is a solution of an equation. So we can take any particular pair, so let's say 1 and 2, and we can plug it into an equation to see whether or not it would work. And when we do the plugging in, of course we put the y into the equation where we have y, and the x into the equation where we have x. So we just replace with the, and then we see, is it still true? And finally, we'll graph equations by plotting several solutions for that equation. So we could get, for example, in this one, we might find we've got a point right, we might find we've got a point right here, and we've got a point right here, we've got a point right here. We don't actually need 3 points. I advocate that you use 3 points because then if there's something wrong, it'll show up, because at least with a linear equation, we should get a straight line. We always do this, a little review of what we've done before. Here we have a set of numbers. Basically, they're our 10 digits that we use. List the Cartesian product R cross R. You know, I'm not going to do that. That's 100 pairs. It would be fun to do, but I suspect you've got more that you'd like to do with your time than list those. Maybe we can think about them mentally for a minute, what that would look like. I'd have 10 pairs that start with 0, 10 pairs that start with 1, and then for each of these, the second member would run through all these digits. Let's just try this, thinking about them mentally. What pairs do I have where x is equal to y? Well, that's actually pretty easy for us to construct, isn't it? There's going to be 10 of them where x is equal to y. Now, when I know that I've got a series going that is getting obvious to the person I'm writing it for, I can do this. And I think you would understand that what comes in the middle here. How about this one? X is equal to 2 times y. Well, that would be true for 0, 0, wouldn't it? It's kind of a weird one, but it is true. And then we could have 2 and 1. We could have, well, we just got integers here, so 4, 2. We could have 6, 3, 8, 4, and then I've exhausted it, haven't I? I mean, my next one I think of is 10, 5, but 10 is not in the set. Finally, xy such that x is greater than 8 then y is greater than 8. All right, so greater than means I can't use 8. Can only use 9. Well, that's a small set. That wasn't so bad as long as I didn't actually list them. Okay, let's just make ourselves familiar again with the Cartesian coordinate system. We have the axes. We've got our x-axis, which runs right here, and our y, let me mark this yellow, and we have our y-axis, which is up and down, and is right here. Our origin which is where they intersect, that's at 0, 0, right? 0, 0. And then our quadrants, we've got 1, 2, 3, and 4. The coordinates of a point, we have our x-coordinate and our y-coordinate. This locates us on the plane horizontally. Y locates us on this plane vertically. We refer to the x-coordinate also as the first member of the pair, or abscissa. Yes, I don't expect you to memorize that, but I don't want you to get through this course and be able to say, gee, I never saw that word. The y-coordinate, second member of the pair, and referred to as the ordinate. Is 3, 1 the same as 1, 3? Well, let's plot it and find out. 3, now notice my scale here. Each of these blocks is 1 by 1, so here's over 3. That's for my x. We're in this zone. And up 1. So where those come together? Right here. So there I go with this one. Now, is that the same as 1, 3? Well, I go over 1, and I go up 3, putting that point there. Definitely not the same. Is the first member of an ordered pair the x-coordinate or, oh, come on. How could I ask such a silly question? You know this. I guess it's always good, especially with the basics, to stress it. Graph the relation. Okay, well, let me clear my Cartesian coordinate system, and we'll go ahead and graph these. You know, I'm going to use a more fun, is this the one? Or is this the one? This is the one. So I'm going to graph with these little smiley faces. Graph the relation over 2, up 1. And then back 1, up 2. And then back 2, down 1. And to the right 1, and down 2. That's an interesting graph. It looks kind of like a square. I mean, at least I've got the corners. I think I've got the corners of a square here. Okay. Okay, here's a little challenge for you. Can you spot the goof? It's coming up. Graph the point on the graph of the equation where x is equal to 0. All right, where is x equal to 0? So if I put a 0 in here, I'll have 5 times 0, which is 0, and negative 2. So I've got 0, and my y is negative 2. 0, and my y is negative 2. So this is the point we're talking about. Determine whether the ordered pair 1, 3 is a solution of this same equation. Well, I know my 1 is the x, and my 3 is the y. So that's going to be, instead of using y, I'm going to put in my value for y. Instead of using x, I'm going to use my value for x. My value for x is 1, goes over here. My value for y is 3, goes right there. So does 3 equal 5 minus 2? Yes, it does. So my answer is yes, this is a solution to that equation. Here are your guidelines for graphing. You might want to write these down. First of all, and it's amazing how many of us, this is including me, don't use graph paper. That's a mistake. You can get a much better looking graph and usually take much less time to do it if you use graph paper, so get some of that. Label your axes with the symbols for the variables. Okay, for example, x and y. Use arrows to indicate positive directions. You notice on mine I've got arrows for the negative directions. Technically, that's not a good thing to do. Mark numbers on the axes for scales. Yes, please. You don't have to do a lot of them, but show what it is for your horizontal and show what it is for your vertical. Whatever you set here, we know applies for the whole range. Plot your solutions and complete the graph. Now please notice you went through these steps before you started doing this. Sometimes my students start here. Wrong place. Label the equation or relation being graphed. In other words, if you are doing y equals 2x, make sure that that is somewhere either on or near your graph. Let's do one. Okay, we're using our graph paper. All right. The axes are labeled. I'm going to shut down these arrows on the negative end. Mark numbers on the axes for scale. These are 1 by 1, so I used a 5 to show that. Now plot my solutions. Without any other indicator of what to do, I usually put 0 in the center for the domain I'm going to try, and then go to positive and to negative. This doesn't always give you a good indication of a graph, but very often it does. In the case of this one, this is linear. I really only need 2 points. However, I will graph 3. I'm going to graph or calculate the -2, the 0, and the 2. When I put a 0 in here, I get a y of -1. When I put a -2 in here, this becomes -4. So I have a -5 altogether. If I put a +2 in, this becomes a +4, and I have a 3. So we're going to plot those points. When x is 0, y is -1. When x is -2, which puts it over here, going horizontally, y is -5. And when x is 2, y is 3. So I can plot this, right? Does that look right? Oh, it isn't right, is it? Because I didn't plot it at 3. When x is 2, y is 1, 2, 3. Now, gee, I'm glad I caught that. Hopefully you would have told me when we were back in class and I could correct that for everybody. So I've plotted my solutions, completed the graph, labeled the equation. Well, fortunately for me, I already had it. But if I didn't, I would write it in. All right, here we've got a quadratic. We're going to do the same thing. 0, -1, -2, 1, and 2. When I put a 0 in, I get a 0 out. When I put a -2 in, let's do it, because here's where people sometimes get confused. So I put a -2 in. What's being squared? Only my -2. So I do that first, and I get minus a, what happens when I square -2? It becomes positive. So my y is equal to -4. And I'm going to do it here as well. And that will be also a -4. This is a -1, and this is a -1. Okay, here's a little challenge for you. Can you spot the goof? It's coming up. I plot those points. One of the things you might notice here is that this is the minimum y value. This is going to be identified as the vertex. When you find a minimum or a maximum in a quadratic, that's going to be your vertex. Okay, it's time for me to come clean. Goof number 1, which you undoubtedly noticed, when you graph this, it doesn't go up here where the positive y is. It should have gone down here. And the other goof occurs right here when I refer to this as, oh dear, a minimum. I don't think so. If you're looking at -4, -1, 0, a -1, and a -4, that is not a minimum. This is, yes, you said it, maximum. And I've got x is -1, y is -1. X is -2. Oh, wait a second. What's the scale? Didn't matter for 0, 0, but it sure matters now. My scale is no longer 1, 1, is it? It's 2 by 2. So when I go -1, I only go to here. And when I go down, I'm in the middle of this block right here. And when I go -2, I'm on this line. And I go down 4, it takes me to here. I can plot those other 2 points. And one of the things, of course, we know about a quadratic, it always plots as a parabola, which has a vertex. The axis of symmetry will run through the vertex, and this will be symmetrical across that axis of symmetry. Now for the second section, 3. Recognize functions and their graphs. You know so many of them already. What do you already know? You know linear. You know absolute value. You studied these back in Algebra 1. You know quadratic. I like to think about the simplest possible linear graph that or function that you could have. Y equals x. It's linear because we're to the first power here. Absolute value, y equals absolute value of x. And quadratic, the simplest one we could have, y equals x squared. So we've gone from first power to second power, and the graphs that go along with these, here's my linear. Oh, that doesn't show up at all. Oh, that's all right. Our absolute value, that looks like this. Forget this. And our quadratic, of course, is a U shape, right? Yeah. Use function notation. Do you remember this? Function f with an input of x equals x. This would be the linear. Function, oh, let me rename it. I'll rename it something else. We won't call it function f. I'll call it function g of x. This function, instead of being linear, is going to be absolute value. So this isn't multiplication of f and x. No, 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 no. It's the name of the function. We're calling the function f, or we're calling the function g. The x refers to what goes into it, the domain. And then I could have function h of x, which you can probably predict what I'm going to do here, is squaring x. So 3 different functions with 3 different operations. This one squaring, this one taking absolute value, and this one a linear function. Find the domain of a function once you know what its formula is. There's 2 basic things you have to keep in mind for domain. One of them is that the denominator may never be 0. You never allow that to go to 0. The other, a square root, x is greater than or equal to 0. In other words, it can't be negative. So we'll take a look at some of these. When is a relation also a function? So all functions are relations. If we looked at it as a Venn diagram, do you remember these? If this were the relation, and inside of it I put functions, we'd have some members which would fall in a function, which means it's also a relation. Others would fall into the relation but not be a function. When is a relation also a function? Remember the vertical line test? If I pass a vertical line, let's use this. If I pass a vertical line over a relationship and I see that I only have one x for every y, then I say this is a function. However, if I had a graph that looked like this, and I apply the vertical line test, I'm okay up to here, and when I get here, I have 1 point at the vertex, and now for every x, I have 2. Or for some x's, I have 2. If for any of that domain you actually get 2 y values, this is not a function. Is not. And we can use the vertical line test to keep us straight on that. Okay, we already talked about that, the vertical line test. If a relation has only one ordered pair, must it be a function? Only one ordered pair. And you remember what the rule is? One and only one y for each x. That's why the vertical line test works. So clearly, if you had only one ordered pair, it would have to be a function. If every member in a range appears only once in the relation, every member in a range appears only once in the relation, must the relation then be a function? Well, I can give you an example of that. Remember what the question is asking about, range. Let's say we're going from negative infinity to positive infinity with this function. And the way it graphs, this, by the way, is x equals y squared. As I'm going up, in other words, if I performed a horizontal line test, who's ever heard of that? We would find that for every member in this range, remember the range is the vertical, I'm getting only one value. But this isn't the test we use for a function. The test we use for a function is right here. We use the vertical line test, and it fails. So our answer is no. The question was, must the relation be a function? Well, it might be, but it isn't necessarily a function. A horizontal line test won't do it for us. Which of the following are functions? So what we're looking for is for every x, there's a unique value of y. So when x equals 1, y can be 1 or 2 or 3. That fails. No. There are 3 values of y for an input of 1. How about this one? For an input of 1, 2, or 3. Now these don't duplicate each other. So if you have x values that are all unique, you don't even have to look further. You can say yes. How about this one? 1, 2, 3. We just say yes. 1, 2, 1. Oh, this one we have to look at because we have 2 values of x. We should have only 1 value of y. No. Functions. Which of the following graphs are functions? Well, we'll submit these to our vertical line test. And forgive me for my vertical line not being a little more exact. Okay, this is looking okay as we go through here, but the moment we get here, what do we got? We have 2 values, 2 y values for my x value. It's failing. So this one is not a function. We'll go back and test this one. This is looking good. I never get two values of y for a value of x. So this one is the graph of a function. Try down here. All right, that one is, and this one starts out looking good, looking good, looking good. Look, oops, as we get to here, we run into problems. If you run into problems at any point, even if it's only 1 point, not. Functional notation. We name a function with a letter. We talked about this right at the beginning of this section. We're going to call this function f. Its coordinate points are x, its domain, and y, its range. Or you could think about it this way: the input, the output, the abscissa, the ordinate. No? Okay, I'll forget those. So we can write it with functional notation. We can say it's function f with input x. So it's exactly the same function, exactly the same graph. The only difference is instead of using y here, we're using the name of a function, function f. And the way we read this, it's function f of x. We say of x because that's the input. The coordinate points are x and f of x. I rarely see it written that way, but technically that's correct. Let's see if we understand this. If function f of a equals function f of b, and this doesn't limit it to any particular point or anything, it's throughout, must a equal b? Now, how would we answer this? Well, whenever we're asked one of these true or false questions, we look for a counter example. If we can find a counter example where this is false, in other words, just one situation where a does not equal b, and yet function a does equal function b, then we would have to say that a doesn't necessarily equal b. Well, suppose, let's try something. Suppose function a is a squared, and suppose function b equals b squared. Well, if I put in here 1, I say a is equal to 1, a squared is going to give me 1. If function b, I say b is equal to -1, it still equals 1. And that will always be the case. So if I'm looking at quadratics, these functions are identical, but I've got 1 for a and -1 for b. So I have to say no. If function f of x equals 0, must x equal 0? Well, let's see if we can find a counterexample for that. How about if function x, what if we define it as x minus 1? So when this equals 0, x equals 1. True? So when f of x equals 0, if I put 1 in here, what will f of x equal? 1 minus 1, 0. X equals 1. So this is not true either. No. If A equals B, oh, I think this is a typo. Sorry about that. This should say A. If A equals B, must function A equal function B. F, yeah, function, you know, I can't think of a counterexample where that wouldn't be true. As long as, you know, function f is defined as something, it's not going to change as we go from f to f. So this would be a yes. Consider this function. It has 3 points in it. All right, here's my domain, right? We have my domain first. That's always the first member. And then the range is the second member of the pair. We usually think of it as x and y. So I've got, what is function f? This is function f. It's just these 3 points. That's all there is to it. So function f of 1, when we put a 1 in, we get a 1 out. Function f of 2, when we put a 2 in, we get a 4 out. Function f of 3, when I put a 3 in, I get a 9 out. So you see how that works? This is my input, and this is my output. Perhaps I should think about my point coordinates that way. This is input. This is output. And in functional notation, it's always the input that is in the parentheses. That's the input, which is coming from here, here, and here. All right, we're going to name this function g. And look what it is. It's a quadratic because it has something squared. Find each of the following. All right, my input, every place I have an x, I'm going to put in a 0. We've got 1 plus, there's an x, plus, and there's an x squared. I'm going to use that same, gee, maybe I can even grab it and duplicate it. Let's see if I can duplicate it. Getting smart here with this smart board. Yeah, that's actually what I'm using. I'm using the smart, well, at least the smart board technology. All right. So when I put a 0 in, I'm going to get 0 squared is 0. It's going to equal 1. I put a 1 in. 1 squared is 1 plus 1 plus 1. I put a negative 2 in. Okay, this gets a little more complicated. I square a negative 2, it gives me a positive 4. A positive 4 and 1 is a positive 5, and then I subtract 2, so that's also equal to 3. On this one, my input, now this is where things get sometimes confusing. Thing to remember is even though it looks different, it follows exactly the same rule. So I'm going to put b square in here and b square in here. The thing that is very unsatisfying about this is the result, because it doesn't come out to be a nice, neat number like we got up here. It comes out looking like this. Domain. Domain is part of the definition of a function. Changing the domain will change the function. The domain, you remember, is this first part in a relation, the first member. If the domain is a set of positive integers less than 6, positive integers, so that doesn't include 0. What does it include? What would this set be? Positive integers less than 6. Integers, so it's got to be 1, 2, 3, 4, and 5. That's the domain. And if the function is defined by y equals 6 over x, we get this set. Let's check it out. So when the domain is 1, I get, so there's my 1. I put the 1 in, put a 1 in, and I have y equals 6 over 1, y equals 6. I put a 2 in, I have 6 over 2, so y equals 3. I put a 3 in, y equals 2. I put a 4 in, it becomes 3 halves or 1 1/2. I put a 5 in, 5 into 6 gives me 1.2. So there, I used the domain, the full domain, 1, 2, 3, 4, 5. That's all there is in the domain, and now I see the function expressed as ordered pairs. If the domain is a set of real numbers except 0, well, that would be an important exception, wouldn't it? Because we cannot divide by 0, so that's worth writing out. X cannot equal 0. Then the function is defined as defined by y equals 6 over x, consists of infinitely many pairs. We were restricted up here to only 5. But if we were using all real numbers, and this would be positive and negative, there's no limit. We're not limited to integers. We can use decimals. My, yes, infinitely many pairs. Find the domain of this function. Well, we did say earlier, I want to go back to that there were certain things we had to watch out for in a domain. Right here. We said that we would not allow a denominator to go to 0. This is the one we're really going to watch out for. This one also applies. We'll get to that later on in the course. I don't think we'll see it today. Find the domain. Is there anything that we can't allow x to be? For example, can we allow x to be 0? Then our denominator would be -1. So 0 would be all right. What's the one number that will cause my denominator to equal 0? What number will cause that denominator to equal 0? X may not equal 1. So we could say all real numbers, and here's a way to write that. All real numbers except 1, a positive 1. That's the domain of this function. Only one number is excluded from the domain. And we're finished. Fini. Kaput.